11-4, number 3? Yeah. And the ace of hearts. So on the previous page, the questions are: the beginning of the magic trick, Great Machini shuffles an ordinary deck of 52 cards shown in a figure on that table, and has the nearest person in the audience draw a single card. Use the sample space for drawing a single card from this deck. Find the probability that the contestant got the ace of hearts.
I don't think that's the same question.
You
said number 3, not number 15.
Thank you. That's 15, number 3. I'm sorry. Thank you. Sorry, I just saw number 3 and I was like, wow, I'm good. No, I wasn't. Here, the computers are chosen at random from the inventory. Find the probability that all 3 will be Acer computers. So I have the outcome. If I were to draw the tree diagram here, and I only care about the branch that's Acer computer, Acer computer, Acer computer, right? So the first one I have it's either an Acer or a Dell. All right. So if you actually did the outcomes, since there's 2 choices for each outcome, there's going to be 8 different outcomes, just like the heads and tails one, or just like the boys and girls one, right? You're going to have Acer, 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 Dell, so forth. So there's going to be 8 different outcomes. So what's the probability all 3 will be Acers? 1/8. Exactly 2 will be Dells. Well, that's going to be Acer, Dell, Acer, Acer, Dell, 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 Acer, Acer, Dell, Acer, Dell. So if I were to draw the picture, I would have 8 different outcomes.
So 3 8s. Oh no, 2 8s. 1/4, wouldn't it?
I want exactly 2 to be Dells. So that would be
3.
This one. Oops, I went to B's instead of D's. This one and this one. So 3/8. Does that make sense?
Yeah.
It's the same concept as the heads and tails or the boys and girls,
I
but
just didn't understand how they got the 8 numbers.
because there's 8 different combinations or 8 different outcomes in the sample space. Any other questions? Question?
You have to write out each outcome and figure out how many there's going to be, or is there an easy way to figure out everything?
So you could use the fundamental theory of counting that says there's 2 options for the first choice, there's 2 options for the second choice, and there's 2 options for the third choice. So 2 times 2 times 2 is 8. But visualizing the outcomes can be beneficial when it says exactly 2 are Dells. My accent comes out when I say Dell computers. So sometimes visualizing it is really helpful with those types of problems to see all the sample space. There might be a question that says, what are the sample space? What is the sample space? And a tree diagram would be handy to come that. Now you don't necessarily have to have a tree diagram, but it's really nice to kind of visualize what's going on. And eventually we'll look at conditionals where tree diagrams are beneficial to see. Any other questions? We've covered 11, 1, 2, 3, 4, and halfway through 11.5. So today we're going to pick up where we left off at 11.5. And I believe we were, did we even start 11.5?
Yeah, we
Yeah.
did.
Okay.
Barely.
Okay. Load this. So last time we talked about probability using combinations and permutations. And we said with really large possibilities, the fundamental counting principle or the tree diagram isn't going to get us too far because we're going to have a huge number of outcomes. So there's no way we're going to be able to list every outcome. We just want to know how many of them are possible. So that's where we're going to have to come to Canley. We're going to have to ask ourselves, is it a combination or is it a permutation? Does order matter? So the first one we looked at was a student selecting 3 books from 15. So we have 10 biographies and 5 current event books. So we had different categories, and we wanted to know what was the probability if she picked 3 books at random that she would get 3 from the current event books, 3 exact current event books. So we broke this up into 2 parts. The first part we had to say how many different combinations were there, how many different ways I could pick 3 from 5. How many different ways can I get 3 different current event books from a group of 5 current event books? So we did that. We got 10, sorry. So there's 10 ways to pick 3 books from 5. Then we had to say how many different ways were there to pick 3 books from 15, since there was 15 total books. And we got 455. So then for the probability step, we took the probability that we get 3 from current events divided by the probability that we got, or divided by the total number way to get 3 from 15. You guys see that? You guys remember doing that? And then eventually we're going to turn these into percentages down the way when we get into statistics. We're going to see, you know, what's the likelihood of it happening. So percentages come in there. So your probability will always be between 0 and 1. But if we look at percentages, we move the decimal 2 places to the right, and we can see that it's going to be 2.2%. So around 2.2% of the time, if you pick 3 books at random from a group of 15, where 10 of them are one type and 5 of them are another type, you're going to get all 3 from the 5 one type. And then we looked at what was the probability of getting 4 aces when drawing 5 cards from a standard deck of 52 cards. And this is where I kind of like to look at the outcome of the picture. This is the way we can get aces. This is the way we can get non-aces over the total kind of cards here. So if there are 4 aces in a deck and I'm picking 4 of them, then there's 48 non-aces. I'm picking 1 of them. 52. Choose 5. So this setup kind of gives you a layout. How many ways can I get 4 aces from 4? How many ways can I get 1 non-ace? Divided by how many different combinations or how many different total ways are there to pick 5 cards from 52? That's going to give you the probability. The top number tells you how many ways the event can happen. The bottom number tells you how many total ways are possible. So if you want to know the probability of the event, take the number of ways the events can happen divided by the total number of ways the problem can happen. So you guys remember doing that? So yeah, we were right here, right? We got out the number, really large numbers, put it in a calculator. It's a very small percentage. It's a very small number. Let me pass on the sign-in sheet. All right, everybody with me now? So this next example is talking about a combination lock that has 40 numbers on it from 0 to 39. Find the probability that if the combination is to unlock consists of 3 numbers, it will contain the numbers 1, 2, and 3 in some order. Assume that the numbers cannot be repeated in the combination. Okay. So does order matter here?
Yes.
So is this a combination or a permutation? It's a permutation, right? So I need to use the permutation formula. I have 40 numbers, right? So there's a couple ways to do, if I want to know total, or we can kind of do the same setup as we did last time. These are the numbers 1, 2, and 3, not 1, 2, or 3. So this should be 40 permutation 3. Because out of the 40 numbers that I have to pick, I'm picking 3 of them, right? That's the total number of ways I can rearrange picking 3 numbers from 40. 1, 2, 3 is different than 2, 3, 4. Or 1, 2, 3 is different than 3, 2, 1. Order matters here. That's why it's a permutation, not a combination. You guys kind of see that? For the total, it doesn't matter what order you go about it. If you find the total first, or you find the probability the numbers come from 1, 2, or 3. So this is 3 permutation 3, right? I have those 3 numbers to pick from, 1, 2, or 3. How many different ways can I rearrange them? It's a permutation, picking 3 numbers, right? How many of the numbers do I want that's not 1, 2, or 3? Well, there's 37 of them, right? But how many do I want to pick of not 1, 2, or 3? 0, right? So this part is a little, you don't necessarily have to list it, but I think it's a good idea, because what if I said, okay, you're going to pick 4 numbers? What's the probability at least, or 3 of them are 1, 2, and 3? Then this becomes 1. It's important to think of the categories. Here, this 37 permutation 0 is 1. Right? Just like on the aces, we picked 4 aces, but we had to remember that we had to pick 1 more card that wasn't an ace. Right? On the previous page, what I put the category aces and non-aces. Well, I had to remember to pick 1 card that was not an ace. It turns out on the permutation of the combination lock, I want to pick 0 that's not 1, 2, or 3. But the problem can easily change to say if you're picking 5 numbers, what's the probability that 1, 2, or 3 shows up in some order? Then you have to remember to put those 2 other numbers in this category. So it's kind of a good practice to always think of that other category, and you can always pick 0 from that category. Does that make sense? The whole purpose is to be able to relate if I can get my pen to come up, is to relate this 40 corresponds to 37 plus 3. This 3 corresponds to this 3 plus 0. Right? How many am I picking from this category? How many am I picking from this category? Divided by how many am I totally picking?
Will that always be the case?
That it will add up like that?
Yeah.
If you take into account all the categories. Like we did on the previous
So
with
they
the
should
aces,
add up.
they should.
Okay.
Now, if you leave this one out, it's not a big deal because it turns out to be 1. But in some cases, it's not going to be 1. Like the ace case, we're picking 4 aces, but we're picking 5 total cards. So we have to remember that there's another category that we want to pick 1 card from, and how many cards are in that category. That makes sense?
So it would probably be better just to go ahead and throw it in
It
there.
is.
Just for practice.
I
and
think
to
so,
know.
just to keep kind of the formula or the system kind of the same. You always want to say, okay, what am I picking from? Here, I want to pick them all in 1 category. So P or 3P3, if you plug that in, you end up getting 6. And if you look at the different combinations of 40 permutation 3, we get some large number, which is 59,280. So your book didn't show that second kind of the idea that there's 2 different categories. One of the categories is the number is 1, 2, or 3, or the other one is a number is not 1, 2, or 3. We just, in this problem, is picking 0 from that category. But if you plug in your calculator here, you should get 6 times 1 divided by, what did we get, 56,000? I don't remember what was it.
59.
Oh, 59.
280.
59, 280.
Yeah.
So it's going to say, there's 6 ways to do this one thing. There's 1 way to do this other category. There's 59,280 ways to do this category. And then the probability is always putting the number of ways the event can happen divided by the total number of ways. So if you kind of set that up, it's all there. And we're going to do some more, maybe where there's some in the other category where it makes sense to write it that way. So we get the outcome or the probability that that's going to happen is 1 divided by 9,880, which corresponds to 0.000101. And that's some things with probability. Sometimes they're just such small numbers, it's kind of hard to relate that.
So would you just say 0%?
Yeah, and so this is approximately 0% or 1/100 of a percent. Okay, so here's an example I think it will make sense where we kind of have those two categories. The store has 6 different fitness magazines and 3 different news magazines. If the customer buys 3 magazines at random, find the probability the customer will pick 2 fitness magazines and 1 news magazine. Right? So I have my categories for my event being fitness magazines, news magazines, divided by kind of total, right? So what would I put in the fitness box?
6 combination 2.
6 combination 2. Yeah, order here doesn't matter. So that tells me it's a combination. And then there's 6 fitness and I want to pick 2 of them. What would I put in the news box?
3 combination 1.
3 combination 1. Good. And then what would I put in the total box?
9 combination 3.
9 combination 3. You see kind of how this helps guide that I'm picking 2 fitness and 1 news out of the total of 3 that I have to pick from. 6 of them are fitness, 3 of them are news, so that tells me 9 of them, 9, 9. You see that okay? So now it's plugging in your calculator with 6 combination 2 and 3 combination 1 and 9 combination 3.
3.
9 comma 3.
84.
84. So 15 times 3 divided by 84. What's that approximately?
15/28. But that means 53.5 or
Point.
0.53. Sorry.
So about 53% of the time, if someone this specific instance is going to happen, right? If it says at least 1 news magazine, you have to then say, okay, well, this is the probability of getting 1 news magazine. Then you have to do what's the probability of getting 2? What's the probability of getting all 3? And then you would add them up together. And we'll do some examples like that. But it's the exact same concept as what we kind of did before with the at most and at least. You have to take them one by one. You guys see that? You see how that comes in handy, kind of breaking it up like that? Your book doesn't do it necessarily that way. Exactly. I mean, they get the same approach. They find the 3 separately. 45 over 28, 15 over 28, which is approximately 0.536. So let's go to the homework and look at some of these. What did I assign for homework? On 1-5, 3 to 15 odd. student faculty government committee of 4 people is to be formed from 20 student volunteers and 5 faculty volunteers. Find the probability the committee will consist of the following. Assume it's selected at random, so equal likelihood of picking a person. So what's the probability that all are faculty members? So I kind of the same setup. I have faculty and I have students over the total, right? I have 5 faculty. I'm picking 4 people. And I have 20 students. And I'm picking 0 of those. I'm going to write this a little better. I don't have too much room here, so all faculty, right? So I have my, and you might need more than 2 boxes depending on how many groups there are. A lot of times there's only 2. 5 choose, 20 choose, 25 choose. So all of them, 1 through 4 on this is going to be the layout for all these problems. I have 5 faculty and 20 students. So this is my faculty, this is my students. For part A, I want all of them to be faculty members. So I do 5 choose 4 times 20 choose 0 divided by 25 choose 4. All of these will be divided by 25 choose 4. Because those are, I have 25 total people and I'm picking 4 of them. If I want the specific outcome that all of them be faculty members, then I need to do 5 choose 4. This is a combination because order doesn't matter. The only time order ends up mattering if it is like a combination law, or if it comes out to be like the first person's president, the second person's vice president. If they give some kind of role to the people, the first person's the batter, the second person's or the first person's the pitcher, the second person's the first baseman, things like that. If it has meaning to the order, then you're going to use a permutation. The combination is kind of the fallback. Majority of the time, it's a combination. Do you guys see that for all faculty? What would change if you want 2 students and 2 faculty members?
You'd say 5 choose 2
Good.
and 20 choose 2.
Good. But the bottom would stay the same, right? All of them being students.
5 choose 0 choose 4.
Good. Because you have to always keep in mind how many are you picking totally. And you're picking 4 of them. So does that make sense? Do you guys see that? 5. We have Republicans, Democrats, and Independents. If a committee of 3 is to be selected from the probability that all of them are Republicans, all of them are Democrats, 1 of each party, 2 Democrats, 1 independent, 1 independent, 2 Republicans, because that's 3 categories. Okay. And you really, on the first one and on the second one, you really don't have to write the 2 other categories, because anything choose 1 is always 1. Or sorry, anything choose 0 is always 1. And if you're picking 0 from that category, it's 1. But sometimes it's just nice so you keep that form for all the parts of that question. Just like what we did up here, and we just changed a few of the numbers. If I can punch that in my calculator correctly, I'm going to get this the right answer. Seven. You're choosing different entrees. Again, you have three contains spinach. A guest will choose 4, and a chef will choose 4. Find the probability that none contain spinach, at least 1 contains spinach. At least 1, that's where that at least 1 comes up. Be careful with that. We're choosing 12, and 3 of them have spinach. So it's kind of the category, this is how many have spinach and this is not how many, or this is how many don't have spinach over how many are totally picking. Doesn't matter that the guest is picking 4 and the chef is picking 4. You still have the outcome. Right? There's 12 total, and you're picking 4. None of them contain spinach, so that'd be 3 choose 0, 9 choose 4. If 3 of them have spinach, then 9 of them don't have spinach, right? Out of the entrees. At least one has spinach. At least one has spinach means 1 or more have spinach, right? So this one, there's 2 ways to approach the at least one has spinach. Do you remember the probability theory that we said the probability 1 has spinach plus the probability 2 has spinach, plus probability 3 has spinach, plus the probability 4 has spinach, plus the probability 0 have spinach, right? If I'm picking 4 of these, this actually turns out to be 0 because there's only 3 of them that have spinach. But the outcome is either 0, 1, 2, or 3 have spinach, right? So the probability 1 plus the probability 0 plus the probability 2 plus the probability 3 of them have spinach is 100, or 100%, right? Those are your only outcomes. You're going to get 0 with spinach, 1 with spinach, 2 with spinach, or 3 with spinach. Because there's only 3 of them with spinach. So at least 1 with spinach, you could find the probability 0 of them have spinach and then take 1 minus that number. You get the same thing as taking the probability 1 has spinach plus the probability 2 has spinach plus the probability 3 has spinach. That's the same thing as 1 minus the probability 0 has spinach. You guys kind of see that? The properties of probability, every outcome, the probability of each outcome individually is going to add up to 1. Right? You either have 0, 1, 2, or 3 with spinach. So if you want to know the probability that at least 1 has spinach, you can find the probability 1 has spinach, plus the probability 2 has spinach, plus the probability 3 has spinach. Or you can take 1 minus the probability 0 has spinach. You're going to get the same answer there. Right? Because you only have 4 different outcomes. And so you can do that both ways on that one and check your answer that it's going to end up being the same. 3 have spinach, pretty straightforward. All 4 have spinach. What's the probability all 4 have spinach? 0, right? You can plug in your calculator or 3 combination 4 and it should tell you 0. You cannot pick 4 objects from 3. So some of that just makes sense in a way. If there was more that had spinach, then we could have more outcomes. If we're picking 4 dishes, then there's 5 possible outcomes. 0, 1, 2, 3, or 4. But in this case, since only 3 of the dishes have spinach, we only have 4 outcomes. 0, 1, 2, 3, or 4. So if I want at least 1 has spinach, I have to calculate 3 different probabilities. Or I can calculate 1 probability and take 1 minus that number. Some of you guys look a little lost.
Can we go through number 3, like each point, so that we have an example of how it looks, like with all the boxes? I know that's gonna take some time.
I kind of did,
No.
because all the form, okay, how many people got number 3 that I went through the boxes? I mean, if no one did, that's fine. I can go over it, but all faculty members, all your setups for each problem, if this is part A, this is what your setup's going to look like, right?
Right.
Right?
That's A.
That's
just A.
This is all of them. A, so let's do, this is all of them. Let's call this one A. I'm going to make A and what I would change in red. What would I change for A? all faculty members. I'm gonna put, I would put 4 here, right? 0 here and 4 here. That's A. You guys see that?
And B, you only change those 3 numbers.
Yeah, and then for B, let's put it in blue. I want 2 students and 2 faculty members. So I would actually only change these 2 numbers. This would be 2 and this would be 2.
So only the top changes
Yes.
and the bottom does not.
Yes.
That's where I'm getting lost, is I want to change the bottom.
The bottom is the total. You can't, the total doesn't change for each event. There's 25 people to pick from, and you're picking 4 of them. So this total doesn't change. Does that make sense? You only change what you want for the event to happen. At first, we wanted 4 faculty and 0 students. So this was 4 and this was 0. So B then changes this way, right? Does that make sense? Why B is that? So C,
Change faculty 2 to 0.
yeah. So C, I want the faculty, I want all students. So if I change 0 faculty, I want 4 students. So 5 choose 0 times 20 choose 4 divided by the 25 choose 4. That will give me the probability there. And then 4, or I've been doing ABC, so I'll just keep consistent with that. Say D, these 2 numbers are the only thing that's going to change. 1 faculty and 3 students. So this becomes 1 and this becomes 3. Make sense? And 5 is going to be the same setup, except you have Democrats, Republicans, and Independents. Your bottom number should always stay the same within the problem. Of course, it's going to change from problem to problem. 7, it's going to be the same thing, except we have spinach and non-spinach. 3 of them that have spinach and 9 of them that don't have spinach. So if I want 0 with spinach and 4 with not, at least 1 with spinach was that example I said where you could do the 1 with spinach plus 2 with spinach plus 3 with spinach, or you can do 1 minus 0 with spinach. And you already found 0 with spinach in number 1. So you should be able to check yourself relatively easy. If you do find 1 with spinach and 2 with spinach and 3 with spinach and add those 3 numbers together, it's going to be the same as 1 minus what you get for number 1. 9. We look for 4 openings, and they're looking to hire engineers and network engineers, database administrators and network engineers. And then we have these 5 different, all network engineers. 2 database administrators and 2 network engineers. All database administrators. 3 database and 1 network engineer. 1 database and 3 network engineers. The exact same approach to students and faculty, right? Looks like 11. Find the probability of getting a triple digit number where all the digits are the same in a lottery game that consists of selecting a 3-digit number. So you're picking a 3-digit number and you want to know the probability that all 3 are the same digit, like 111, 222, 333, 444. So you have to have how many 3-digit numbers are there possible? Like, so 3, I don't know if you're answering the right one. How many 3-digit numbers are possible? The total number of ways to get a 3-digit number, right? If I take 1,000 minus 99, that give me, or not, right, 90, those would be all the 3-digit numbers. 100 is a 3-digit number, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110. 111 fits the event that all the digits are the same, right? So 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, 5, 5, 5.
But I wasn't.
Oops. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Divided by how many total 3-digit numbers are there? And that's what it's asking there. So there's no permutations or combinations there. It's just a problem of thinking how many fit the event divided by how many total numbers are there in that event. The choose 5 at random for a morning schedule. Find the probability that 3 are going to pay by using workman's comp and 2 Medicaid or Medicare patients. Exact same approach, students, faculty, spinach, no spinach, Democrat, Republican. It doesn't really kind of matter the category. It's the same setup. So here you're looking for the specific instance that you're picking 3 worker comp and 2 Medicare out of your total of 5 you're picking from. Same setup, box, box divided by box. How many do you want from this category? How many do you want from this category? And how many total do you have? And how many of those do you want? Make sense? Kind of seeing a little bit more of the problem.
So that would be 12
So
total.
12 total. So I have 8 workman's comp workers. I want to pick 3 of them times 4, choose 2, divided by 12, choose 5. On this one, the only time it gets a little bit interesting if I say at least or at most. Because that's when you have to think, if I say at least or at most, you have to think of what other conditions satisfy that. Right? Here, there's the outcomes. Right? I can either have 0 comp caseworkers, but since I only have 2 Medicaid patient, or how many do I have? 4. The outcomes are either here. There's quite a bit of them. I could have 5 comp caseworkers and 0 Medicare. You could have 4 comp caseworkers and 1 Medicare, and you can go down like that to see the different outcomes. Sometimes an outcome's not possible. Like here, I could not have 5 Medicare patients because I only have 4 in my pool.
It's
Question.
usually always listed like that, where the total of the specific group is listed in the front half of the phrase, and then what we're actually picking or choosing is in the second half.
Generally, it will say, generally it'll give you the statement, and then that's the question.
Just to kind of like help us set it up.
Yeah, so this one, here they give you, more options, and so you can kind of divide it up from the statement to the question. This question, this question, this question, this question, but I could just copy this and paste it in there, and it would be kind of the same setup. Okay. But sometimes students kind of like it like this because they can kind of tell the difference between the statement and the question versus here it's a little confusing. What is it actually asking me? But if I put a space and says part A, it'd be a little clearer. Question?
Okay, so when we set these up, all we do is just first decide, of course, whether it's combination or permutation. And then we take the number on the left side will be our numbers from our different categories that we have.
This is how many you have in the category, and this is how many you want from that category.
Right,
Yes.
okay. So the left side will always be how many,
You
the
have
right side will be how many we want.
Mm-hmm.
Okay.
So that's why if you add this number and this number, you should get this number, and this number and this number should get this number,
Okay,
right? Because you want to pick 5 total,
right.
3 from this category and 2 from this category. You have 12 total, 8 of them are in this category and 4 of them in this category. Kind of a quick check that your numbers work out right. Visually, if you write it like this. 15, we did an example in class. Combination consists of 3 numbers in specific order with no repeats. Find the probability the combination consists only of even numbers. Right?
That's permutation.
It's a permutation. The category, instead of before we had category 1, 2, or 3, now we just have how many even numbers do we have and how many of those we want to pick from. Right? So we have 20 numbers, 0 through 39. Is 0 an even number?
I don't think it counts as either one.
I thought it was neutral.
Well, the definition of even is it can be divided by 2. 0 can be divided by 2. But odd, good question. Let's see. Satin is 1 prime. 1 is not prime, but it is odd. Is 0 even? Yeah, so it is even. FYI.
Now ask it if it's prime. Or
0?
Odd.
Is 0 odd? It is very odd because it's 0 now.
Oh, it's 'cause
Okay,
you're
Google.
You're in the news category.
Oh, I don't know. Oops. Even.
So it's
0 shall have the properties of the characteristic of an even number. So default, if you can divide it or if you can multiply it by 2, it is, sorry, if you can divide it by 2, it's even. If you can't, it's odd. So by that definition, 0 is even. Isn't that odd? No, okay. I know. It's the way they pay me the big bucks. Okay, so we finished 11.5. So 5 minutes, 11.6, since I give you guys the handouts there. Now this book, we're going to odds and expectations, which a lot of times you see things published as odds. Crime statistics are a lot of times published as odds. The odds you'll be a victim of a crime. We're going to look at computing the odds for or against something, right? So there's keywords, the odds in favor and the odds against. They're going to be very similar, but you're going to be very careful the way it's worded. And then we're going to look at computing odds and probability. They're very closely linked, and a lot of students kind of forget, especially in this book, because they write them the same way, which I try to avoid. And then compute probability from odds. And then we're going to look at an expected value. I hate this in this book. It writes it like this. Most places write it like this. Your book introduces it like this. When they publish it, they usually write A colon B, or they'll say A to B or B to A. I don't like it like this because this looks just like a probability, right? And it gets a little confusing if I see 1/2. I think, oh, that's a half. That's a probability. It could be 1/2 odds, but that would be the probability of 1/3. And we're going to get to that. But I prefer to see it this way. That's why there's no confusion. This is an odd, and if it looks like this, it's a probability. So the next kind of odds are used in casinos, racetracks, other gambling establishments to determine the payoffs when bets are made and lottery tickets are purchased. If you go to play roulette or various different games, it'll tell you the odds of winning, and the odds are supposed to be tied to the payoff. If there's a 1 in 17 odd of winning, if you bet $1, you should get $17 if you win. So a lot of times they're written that way, that would be a probability of 1 in 18, right? So we're getting there. There's 3 different ways your book says they can write odds. I hate this way because it looks like a probability.
So you won't use that way.
I won't use that way. Odds are, yeah, generally, if they say, you know, be very careful with how they say odds in favor or odds against. Right? So here they say the odds against Pittsburgh repeating a Super Bowl championship is 9-1. They could say the odds in favor is 1-9. So order here matters. If they switch it for or against, you can switch the order. So the odds of and the odds against. So by setting the odds at 9-1, odd makers are predicting that if they play 10 times, if they played the Super Bowl 10 times, that they would win it 1 out of the 10 times. So this would be the number of times they would win it out of the total number of times they would lose it. Sorry, number of times they win it out of the number of times they would lose it. Together, you add them up, that's the total number of times they'll play. Odds in favor is the number of outcomes you think for it to the number of outcomes not for it. The difference in probability, we always put the number of outcomes for it divided by the total number of outcomes, right? So let's look at this example. Card is drawn from a standard deck of 52 cards. Find the odds in favor of getting an ace.
What's the difference between odds and probability?
So what would be the probability here? 4 out of 52, right?
Yeah.
4 out of 52. 52 is the total. The odds are going to be 4 to 48. This is the number of not aces. Right? If I add those two numbers together, I get 52. The first number is generally the same, right? There's 4 aces and there's 48 not aces. So the odds of getting an ace is 4 to 48. Does that make sense? 4 of them are aces, 48 of them are not aces. You can simplify that to 1 in 12 if you divide both sides by 4. So simplification works in that manner. You can reduce that down.
So really, you just slide over what you're looking for out of the total, sort of.
Yeah, and I'll kind of write this A to B. The probability is going to be A over A plus B.
Okay.
If you have the odds to find the probability of the same thing, or it could be B over A plus B, depending if the odds are for it or against it. And we're going to get there where when we convert probability into odds. Because if you have one, you have the other. You can get the other. What about B? The odds against getting an ace. 48 to 4, right? 48 cards are not aces, and 4 of them are aces. So the odds against getting an ace would be 48 to 4. The probability, what would be the probability? It would be 48 over 52. The probability of not getting an ace. 48 cards are not aces over 52. You guys see the 48 and the 4 and the wording, the probability in favor of and the probability against. The order matters. The first is either getting a card or against getting the card. Okay, so I think this is a good place to kind of stop at 11:05, and we will continue this on, and you can force simplify it. You can, we'll, again, I kind of do not prefer this because it looks like probability. And the probability is actually 1 over 13. And the odds is 1 to 12. So if you prefer, you write 1 to 12 for odds, or write it like this. Just so I can clearly see, okay, you're calculating an odd. If you make a mistake, it's only give you points for knowing it's an odd and not a probability.
Did the sign-in sheet go around?
Yes.
One o'clock.